All right. Hello, everyone. Happy Wednesday, wherever in the world you are. We are going to go ahead and get started. If you haven't been to a webinar before, or if you're returning, hello again. My name is Heather Grant. I am one of the community admins in the maintenance community by Upkeep. Thank you so much for joining today. If you are not already a member of the maintenance community Slack group, we would love to have you join us. We will add a link on how to sign up in the chat shortly. Today I have with me Evan Zabowski. Evan, thank you so much for being here. Really looking forward to our conversation today. The recording from today's session, as well as a summary of this presentation, will be available in the maintenance community Slack. Summary of the presentation, meaning just a version of these slides. If there is anyone else who you know who would benefit from learning from this information from Evan, please feel free to forward either the recording or a copy of the slides over to them. Joining the Slack group as well. Last piece of housekeeping before we go ahead and get started, you'll notice that Evan and I are the only ones with cameras and microphones turned on today. If you want to ask or answer any questions of Evan, and I know we have a couple of audience engagement questions throughout this presentation, please use the chat feature over on the right-hand side of your screen. I'll monitor those questions and I'll be sure to chime in as appropriate throughout the presentation. And if we have a couple of minutes at the end, we'll go ahead and answer some questions. Otherwise, we will take the rest of the questions offline. That is it from me. Thank you again, everyone, for being here. Evan, I'll hand it over to you to start with maybe an introduction to yourself, how you got involved in the maintenance industry, and then taking us through how to read an oil analysis report in 2 minutes or less.
All right, well, thank you, Heather. So I have a little more than about 25 years experience with oil analysis directly. I've worked for a couple of different oil analysis labs over the years, and I guess, if you want an interesting story, and I'll try and keep it short, for how did I get involved in this world, in this side of the industry, I would say it started, not to make it sound like it's going to be a long story, it started when I first was enrolled in kindergarten. My parents decided to enroll me in French immersion classes, so I was taking all my instruction completely in French all the way through to high school. So I do speak French as well as English. But anyways, once I attended university, I went into chemical engineering, and through fun series of events, the way the world economy was going at the time, by the time I graduated, jobs were not aplenty. And my graduating class had 42 people. 6 of us got a job in our field within the first year. I was not one of those 6. So I re-enrolled for 1 more year, and I managed to earn 2 diplomas in that last year because of all the credits for all the previous classes I had taken. But I decided I'd take a more aggressive approach finding a job because it was such a dismal failure the first time. So I remember that it was Halloween, and I sent out resumes to anybody and everybody who seemed to be hiring anything related to chemical engineering. And just to give you an idea, time frame wise, it was St. Patrick's Day when I got my very first and only callback. So they said, would you like to come in for an interview? Of course, I was absolutely desperate. So I said yes. And I show up to the interview, and they're interviewing me, and it seems like it's a lab position, like actual laboratory work. And we get to the end of the interview, and they said, yeah, we'd like to offer you the job. And I was sitting there going, I don't know that I'm really qualified to do this. I said, I took chemical engineering. I didn't take chemical technology. I'm not a lab person. And they said, oh, well, we can teach you that part. I said, but at the bottom of your resume, under additional skills, it said fluent in French. I said, you're really fluent in French, right? I said, mais oui. So they said, we just won a national contract. It requires bilingualism. We need a French person on staff. And I said, okay. And I said, I guess I can work in the lab. And then I asked that stupid question I should have asked way before, and said, what kind of lab is it? And they said, tribology lab. And I said, okay, I'll be there Monday. Didn't even ask what tribology was, but it was a used oil analysis lab, and that's what got me started. So it's become my passion, and that's why I'm here today. I want to share that passion with you if I can. By teaching you, yes, as the title implies, how to read a report in 2 minutes or less. So to get us started, just dive right in, without even worrying about teaching you anything yet. Let's go through an example, and let's do it the old way. The way I find a lot of people read reports when handed an oil analysis report, the first time or even sometimes the 100th time or the 1000th time, they look at these reports and they're a bit lost. So the first example I'm going to show you is split across 3 slides just to make sure it's nice and readable for the audience. So basically we're going to look at the top half of the first page, the bottom half, and then we'll look at the flip side, what's on the back of the page. And like I said, the way most people do it, if you don't, great. Maybe you won't have anything to learn from this webinar. But if you're doing what I'm about to do, you definitely need to listen to what I'm going to tell you after the fact. Because the way most people read reports is they start at the first page here. So here's the top half of the first page. And their eyes immediately go to, things like the comments. They read the comments and see what did the lab have to say about this. And then, of course, they go to anything that's highlighted. So they look at this one here and they see the high iron and the lead. And perhaps you start interpreting where that iron and lead could be coming from. I mean, it says right here it's an anti-friction bearing is the source of the sample. So you start wondering about bearing wear, shaft wear. Maybe your mind goes to a bunch of those things. As you continue down the report and you go to the bottom part of the first page, you start seeing other things like this one's got a high particle count, it's got some water in it as well. You really start to make some judgments is usually what happens. By the time you flip over to the back page where the ferrography would be reported, you start seeing a lot of information here about all these different wear materials that have been found and even dust and dirt. And by the time you've read through, and most oil analysis reports have somewhere between about 30 and 50 pieces of information on them per sample. So when you start looking at the history as well, you start dealing with hundreds of pieces of data. And most people get a little bit overwhelmed and they've either lost focus or they've been focusing on the wrong thing the whole time. So that's usually how I see people reading reports. And there are 3 very common mistakes I find that they make while they do it that method. So here, let's go through the 3, sort of top mistakes that they make. So now that I've shown everyone this report, maybe you made some of those mistakes. So here's what I'm guessing. Did you start trying to figure out where the iron and lead came from right away? Well, that's mistake number 1. You got to wait for the whole picture. When you don't wait for the whole picture, if you try and interpret on the fly, you're wasting time, right? It doesn't necessarily matter where the iron and the lead came from. It matters why the iron and lead are showing up. Right? It's not a mystery in an anti-friction bearing where the iron and lead could be coming from. I mean, they're going to be the shaft and the bearing materials. Question is, what if it was, a misalignment, an imbalance, or something, absolutely horrifically wrong? So that's one of the key mistakes I find people make is they get bogged down in every new piece of information they read. They start trying to figure out how those pieces all fit together. It's kind of like doing a puzzle and picking up every piece out of the box and trying to picture what the whole thing is going to look like every time you pull out a new piece, rather than trying to lay them out and sense some sort of pattern first. Another key mistake that we make, though, is that a lot of people would read that report and they'd come to this judgment. They'd see that very, very high particle count and they would immediately say, you know what, I think the oil's too far gone. Probably should just throw it all away, change it, get new oil in there. This is mistake number 2. The oil is in fact dirty. I'm not disputing that, but you're addressing a symptom, not a cause, right? Just by changing the oil is not going to save the bearing. It got dirty somehow. So you need to really figure out why did it get dirty and fix that as well. I mean, I'm not saying don't change the oil, but I'm saying simply changing the oil doesn't fix any mechanical issues. So there are just, in my general opinion, far too many oil changes that are prompted based on an oil analysis report that aren't effectual, right? Really what we should be looking at is maybe it's got a breather that looks like this, right? And it's just letting in a ton of dirt. Who knows? And the third really common mistake that I find people making is that they get to the end of the report, they see how bad things have gotten, and they think there's no hope, right? It's too far gone to save the oils, too far gone to save the bearing, whatever way they want to look at it. And this is why I'm going to show you how to read a report in 2 minutes or less, because if we take the time to read every report, even the ones that are normal, even the ones that show up green or have a check mark or have a low rating on them, we will be able to take that data, and this is the big point here, turn it into something that is truly predictive and anticipate a failure rather than being reactive. And that's what I always, compare oil analysis to is that when you wait for the alarms to go off, right, you wait for the report to come back with a whole bunch of colors on it or a high rating or whatever format your lab uses, you've waited too long. And at that point, you may be in a position where, yes, the bearing is too far gone or the oil is too far gone and there's nothing you can do to save it. And so my analogy is it's kind of like using your smoke detector to tell you when your muffins are done when you're baking in your own kitchen. Right? It's just too late. You need to be better at this. And you've probably heard this saying a number of different ways before, and I'll just paraphrase it here anyways. But oil analysis is a tool, and the expression is it doesn't matter how many tools that you have, it doesn't matter how many reports you get, how many samples you've been taking, whatever way you want to look at it, it doesn't matter if you don't know how to use them, right? They're never going to be enough. So, a lot of people have seen a graphic like this before. It's reasonably humorous, but it's very true. And this is one thing I find a lot of people stuck with is they've got mountains of oil analysis data and they haven't really truly prevented many failures. They simply documented their failures as they've happened with an oil analysis report. So we need to not do that. So with that much of an introduction, let me get right into it then and tell you how should you read an oil analysis report. And I'll warn you, this is going to sound very, very simple, and therefore you're going to think it's very easy. It takes a bit of training to do it. You gotta work at it a little bit. Practice, of course, makes perfect. So we're going to go through 2 examples following the steps I'm about to give you. And there's only 3. It is a short list. Step number 1, you need to sort of decide here who is doing this interpretation and why, right? And the very first step begins with understanding a key difference here. So when you're deciding who's ultimately responsible for this interpretation, there can be basically 2 people. There can either be the lab that you hired to do the analysis in the first place, or it falls on the end user. That's kind of the 2 people I'm thinking of here. And when you consider what does the lab have, what sort of stake do they have in this game? The lab has a lot of expertise. Now that expertise is focused though. They understand test limitations. They know which tests can tell you what and to what extent and with what amount of variability or repeatability, those kinds of things. So this is something that they can use to their advantage to understand when they see a number change, does it really amount to any change, or is that just noise within the method, error, within the method as well? They have some knowledge of the equipment metallurgy, right? They know what wear metals come from what sources. They have an idea of, narrowing down to a small degree what parts are actually suffering from the wear. Another big one, though, is trending. This is where most labs really start to shine, right? The average person reading an oil analysis report is always looking for a threshold value. They just want a limit, and they always ask that question, what's the limit? How much iron can I tolerate before it's a problem? And really what you should be asking is, when does my iron look like I'm about to have a problem, right? You'd rather know that. You'd rather anticipate the problem, like I said, be predictive, than simply cross a threshold, which is being reactive. So labs are pretty good at trending data and knowing what trends seem normal versus what trends seem abnormal. So that's kind of what they bring to this game. The other perspective, though, wipe that list clean for a second here. Let's look at it from the end user's perspective. What do they bring to the table? Well, they know where and how samples are taken, right? This is a key part of what they understand, that the lab doesn't generally have a good idea what's going on here. So when the lab sees a report that has a sudden spike in water content or any form of particulate contamination, they take it as gospel, and they'll send out a report saying, looks like you've got really high levels of whatever it is. But the end user might know that they sent somebody different to collect that sample, and therefore they may not have flushed the sample point correctly. They also know that maybe their sample point is at a low point where stuff is likely to accumulate anyways. So they may look at this anomalous report and be able to discount it and say, maybe we should just resample that. Another thing the end user knows is they know all about their equipment configuration, right? They know if it shares lubricant with another machine, if it's got a filtration system, all kinds of things that could factor into why the results are changing, right? For better or for worse. So this is an important aspect that, again, the lab can't necessarily know. End user also knows about operating conditions, right? They know if that machine has been running hot lately. They know if it's in a contaminated environment. They know a lot of things about that machine that, again, the lab can only guess based on the results. And a big key one here, this is kind of an interesting one. They know if there's been recent maintenance activity, right? And that can include oil changes, it can include top-offs, filtration, maybe a part was replaced somewhere in it. These things can all skew the data significantly, again, for better or for worse, and the lab can only guess at why the data has taken sudden changes. So when you consider this is where I'm coming at, that I think it's really on the end user to do the analysis do the interpretation of the analysis and not rely simply on what the lab had to say. So that's why I focus on this about how to do it in 2 minutes or less, because end users typically don't have a lot of time they can devote to this. So I've broken it out, as I said, into 3 steps for what the end user should be doing. And hopefully many of you are end users and going to benefit from this. The step here that we begin with is a very, very simple statement: read the whole report. Now that sounds easy, but it's harder than you think. For one, not a lot of people understand what I mean by the whole report, which you'll see when I go through an example, that I really do mean everything on the report. But here's the key thing. Don't waste your time interpreting as you go. That's not what you're looking at. You're just trying to read through the information and see what's there. I'm also emphasizing when I say read the whole report, I'm meaning every report. Like, a lot of people, when they read a report and they see, it's green across the top, or it's got a really low rating or a thumbs up, a check mark, whatever it is that your lab uses, they stop reading because they go, well, this one's fine, I don't need to read it. No, read the whole report. It doesn't matter what kind of report it is. You can read every report, all reports. And here's the key thing. As you read the report, step 2, all you have to decide is there abnormal data? And by abnormal, I just mean data that doesn't look right. Too high, too low, not consistent with the trend, whatever reason you have for doubting the data. Anything that says, I don't think this looks right, that's the data you focus on. Now, here's all you're going to do, though. You're not going to, again, make any interpretation, not make any judgment on that data other than simply classify it as a cause or an effect. And when you're deciding if it's a cause or an effect, you're not deciding what is it causing, like what effects does it have. And if you're looking at an effect, you don't decide what caused it. You just group it. Is it a cause or is it an effect? And I'll give you a big clue here. Where is almost always an effect, right? Something is making it wear, right? Could be an inadequate lubrication level. Could be too low of a viscosity. Could be contamination. Could be overheating. Could be a lot of things. We're not here to decide that at this moment on step 2. All we're trying to decide is that's just an effect. Something else is driving this. And we're trying to narrow down the report to just the causes. Now, as we go through the report, you're going to find that maybe we'll find a lot of things. We might even find that some of them are causes, not all of them are effects. But no matter how many causes we find, I can assure you that generally speaking, you can group all those causes together in 1, maybe 2 groups. They're almost always interrelated if you've done it right. And the last step, here's the easy thing to do, is now once we've got it narrowed down to just those causes and effects, all we have to decide then is, with that group of causes, what should we do next? Are we confirming the problem, as in we need to go out to do an inspection, a verification to confirm what we think is going wrong is in fact going wrong? Do we eliminate one of those possibilities, right? It's the confirm or deny kind of argument here. We, again, maybe send somebody out there to go check it and say, look for this. If it's not this, then I need to think of something else. Or sometimes it is that third one and we actually know exactly what's wrong. Maybe we've come across this before, maybe it's just blatantly obvious, and we can repair it right away. What I'll emphasize and stress, though, is, again, changing the oil, not usually the best answer. I'm not saying it's never the answer, but it's one of those things I find myself up against many, many times, is people will look at a report, see bad data, see a lot of things wrong, they will change the oil. Now the next report comes back and they'll see most of those problems have gone away. So they think they're doing it right. Well, you just wiped the slate clean was all you did. You eliminated the evidence, right? You didn't prevent the crime, you just swept away the evidence. So we need to be cognizant that when we decide what to do next, that we're doing something that makes sense and not eliminating just the evidence that is actually happening. So with that, let's return to that first example. Let's use those 3 steps, thinking that we're the end user now reading this, and walk ourselves through this report. Now, this example will take longer than 2 minutes, but by the time we finish it, you'll see how it works. You'll see how you have to kind of train yourself to really pay attention as you go along. But by being methodical, we can do it quickly. And so after we do this example, I will get into a second example, and we'll do that a bit more in real time. It'll still take a little bit longer than 2 minutes because I'm going to have to say everything out loud that you normally think, but you'll see it's a pretty efficient way of getting through the data. So to get started, again, let's reacquaint ourselves with this, this first page of a report. Now, depending on where you get your results, reports can be formatted a little bit differently, but by and large, most oil analysis labs produce the same kind of data. So one of the things we should be aware of on the report is there is something called a new oil line. And this is reference data for the oil that you claim to be using. Now, just for everyone's edification, most labs, the way they work at this is that information is populated by sending in a sample of new oil. So it may not be your new oil, right? It may be that another customer of that lab sent in that sample to produce that data. It may be that it's out of date. It may be that no one sent it in. It could be blank, that new oil line. But like I said, most labs are pretty good that if somebody can send them a sample of what is labeled clearly as virgin product, they will save it in their database in a way that it can be printed on every subsequent report that calls for that same oil type. So that is meant as your reference, right? So sometimes people call it the reference line or the new oil line, but it's your reference. It is under best case scenario, what should that oil look like, right? Brand new, right out of the drum, right out of the bottle kind of thing. When you look beside that data, you will see the most current sample. Now, again, some people orient the reports in landscape versus portrait, so it's the line below rather than the line to the right or the left, but whatever way you want to look at it, there's a new oil line on reports typically, and then there is your current sample that you're looking at, and this is the one we will focus on. Everything else further away from that baseline reference, though, is older and older data. So when you read the report, you're looking at that trend. So in the case of this example I'm going to walk you through, to see the trends, you read actually from right to left. And you can see the trend all the way up to the current sample, and then you can, of course, compare that to the new oil reference. So that's the layout of the data. But now let me walk you through the report using our 3 steps. So now that we've covered that, and I'll just, I'll turn on my laser pointer here so you can follow me along, you know where I'm going. So when I say read the whole report, I am actually starting up here in this section. I'm not jumping to the data right away. I am reading the whole report. So what does this report says? It says it's an anti-friction bearing, right? I'm familiarizing myself with, okay, I know what that kind of machine looks like. The next line down, though, it mentions it's an AW46 oil. Now, if you know your oils, and you know about oil analysis, you might know that AW stands for anti-wear. And you might know that the most common form of anti-wear additive is the ZDDP, which is zinc dialkyl dithiophosphate, is a huge mouthful, but in the world of oil analysis, it means it shows up as zinc and phosphorus. So I've only read a couple lines out of this report, and I can tell you right away, I'm expecting to find zinc and phosphorus in relatively equal proportions on the report, just by knowing it's an AW oil. It also said it's a 46. That means it's a 46 centistoke oil when measured at 40 degrees Celsius. Now, again, I'm only knowing these things because I'm familiar with oil grades and general additive chemistries, but I'm interpreting them as I'm going here just enough to say I have an idea what to expect later. So I read, it's an anti-friction bearing. I read the oil type. You can see the make and model. You may not be able to get anything out of that. But look at sump size, though. Right, sump size. Is this a half-gallon reservoir where it's really easy for me to go in and just swap out the oil if there's a problem? Or is it a 50-gallon reservoir where I'm going to try and save that oil, and maybe I'd be looking at different interventions like filtration or bleed and feed to keep this machine at peak operating condition? Right? Just little things to consider as you read the report, right? So read the whole report, top to bottom. Now, if I move over here, this sample information is just, what day was the sample received by the lab? What day did the report go out? Who commented on it? What was the package? There's not much there. You can pretty much glance over that in a second or two. But your eyes keep going and you come over to this section here where it says customer information. And I know it sounds really, really dumb to say this, but read it. Right? In there, you should see your plant's name and your name. Because, and I mean this kind of jokingly, but it's true, if it isn't, you're already done reading the report because it's not your report. Give it to somebody else. But no, in seriousness, you read it because you need to familiarize yourself with which plant are we talking about. Many, many people monitor multiple locations. They should be aware of exactly which plant they're looking at, just so they're not making any presumptions, that are incorrect. But we keep reading the report. We're going to come down to this section now here. It's a list of the problems, just a list. So it says this one's here, got, water content, wear, and particle count. If we move over to the right here, you're going to see comments related to high wear, particle count, and water. No mystery, that is very true. And an interesting question I get frequently, and have had this many, many times over the years, is people often ask, how are those comments put there? And the reason people ask is because they have a suspicion. And their suspicion is that a computer does it. And you're partly right, but you're not always completely right. Most labs worth their salt have what we call human eye review, meaning a human actually read your report before it went out to the end user. However, yes, most labs employ a system whereby the comments are what we call canned comments. They're pre-written. And people ask that question all the time because they're doubting the validity of a comment that was pre-written, just pulled from a list of pre-written comments kind of thing. And the point is, well, they are pre-written to save on time. They're pre-written to make sure they're worded correctly and clear. But that is, to be fair, the downside that sometimes they're a bit middle of the road. They don't necessarily hit the nail on the head for this exact component and this exact type of facility in this exact industry. That's a fair comment. So I do tell people that yes, they are pre-written, but humans do generally, like I said, most labs use humans to read the report and make the interpretation, select which comments go there, and they will be inserted. So you will see standardized wording, you'll see a lot of repetition, and you won't see anything really, really specific most of the time. Now, that's not to say the comments aren't valuable, but it's also to say the comments aren't the end of the world, right? If the comment was perfect, and the comment included everything you needed to know, why would they bother printing all the data? Why would they take up more pages than they needed to? Right? The comment is merely guidance. It's still up to the end user because, as I pointed out, the end user knows a little bit more than the lab does to come up with a final determination. And just while I'm on the subject, share you a quick little anecdote for you. It's one of my favorite complaints. If people phone in to complain, and they've been looking at their last few reports, and they look at one like this one, and they see all these comments. They look at the one they got before, and they see the same comments. They start to think that we're really not doing much work because we just put the same comment on the same report twice in a row, sometimes 3-4 times in a row. And so when they phone in to complain, this is my favorite complaint. I love this complaint, really, I truly do, because they'll phone in and they'll say, "You keep putting the same comment on the report," and I just kind of put it back on them and say, "You keep not fixing it. I mean, I don't know how many times I need to tell you what's wrong. You keep not doing anything to make it different. So yes, you're going to get the same comment." But anyways, we read the comments from the lab because we want at least one perspective about what we're going to see as we continue down the report. Like I said, it's not necessarily that the final answer will be found there, but we can agree or disagree with it as we continue to go along. So here's the part where it gets really tricky. This is when I say read the whole report. This is where a lot of people skip still, even after seeing what I've done so far, that I read everything across the top, read everything in the middle section there. They don't read this section here, where we see information regarding the samples. So if you look again, like I said, you start at the very far right, will tell you the oldest sample on this report. Well, this one here, you can read the date on it. You can see how long it took before the next sample was taken. And that one happens to be about 2 weeks later. And then you can see when the next sample was taken was about 4 weeks later, and then 4 weeks again. You have an idea what the spacing is between these samples. You have an idea what that trend is going to look like: 2 weeks, 4 weeks, 4 weeks. As you read down the information, you will see the hours are reported down here. That very first sample's got no hours on the oil and no hours on the machine. Would you just learn? It was a brand new bearing on that day. Now, as it continues to age as a machine, the oil ages at the same rate. Now, of course, that's to be expected, but we never see the oil have lower hours in the machine. So what did we learn? The oil's never been changed. So again, one of the things we're learning here is that with this trend, not only do we know that the first interval is shorter than the next intervals, we also know there should be no reset to any of these values, right? Because the oil's never been changed. So I read this and I'm anticipating what I'm about to see. So I've spent maybe 30 seconds in the top of this report seeing this kind of information before I get to the actual data, because the point is once I get to the data, I'm going to be very, very quick. I should be going cause, effect, and just moving right along. Now, we'll take it a little bit slower because it's our first one together, but you'll see what I mean. So now that we're actually going into the data, I've already got in my frame of mind, it's a bearing, it's got, I don't know what size sump, but I know what the pattern is for samples. I know what the pattern is that there's no oil change. I've got an idea what kind of trend I should be looking at, right? I should see everything slowly increasing steadily, right? We have fairly steady intervals. I should see a fairly steady increase in all the things that are going to increase, and I should see a fairly steady decrease in anything that should be decreasing. So with that, let's look at this one. So as I said, in step 2, all you have to do is decide, is it an abnormal piece of data? That's it. So what's the first thing that comes out as abnormal on this report? Well, it's probably iron. So let me turn off my laser pointer here because you don't need that anymore. So it's probably iron. Now all you have to do is decide, is it cause or an effect? Don't interpret any further. Don't try to figure out what's causing it. Don't figure out what else is going to happen. Is it a cause or is it an effect? Well, like I said, as a clue at the beginning, wear is usually an effect. Something is making it wear. So we're going to list iron here as an effect. And we go back to the report. Next thing we find that's abnormal, well, it's probably going to be that lead, right? It's jumped up as well. And again, we decide, is it a cause or an effect? So where do we put it on this list? We're just going to list it as an effect. Now we keep going down the report, and the next thing that jumps out that some people will point out to me is they don't like some of the additives, right? They'll stop on calcium as an example and they'll go, wait a minute, calcium value doesn't look like the new oil value. And I'll go, okay, do you think that's a problem? And of course, most people will answer yes. If it doesn't match, it's not right. And I go, fair enough. I said, because I read the whole report, though, I can tell you why I'm not worried about the calcium. Remember, the very first sample on the right-hand side was at 0 hours, meaning it was a brand new machine with brand new oil. Now, if you look at the calcium value on that very first sample, it was substantially lower than the new oil value. And if you look at the trend of that calcium up until the current sample, what do you notice? It's a flat trend. So what can I deduce? Well, there's 2 different ways you could deduce what's happening here. If you wanted to pause for a moment and interpret on the fly, which I wouldn't recommend, but let's do it for sake of this one, just so we don't get too many questions, people wondering why we're going to ignore calcium. There's 2 ways that I could have the new oil calcium be very, very different than all my used samples. One way would simply be that that new oil reference is out of date or incorrect. It could be that this is in fact not Conoco AW46 as it currently looks like. And that's why my data doesn't match it. Another more plausible explanation, though, is because this was a brand new bearing, it is what we would consider to be factory fill, not shop fill, right? Maybe Conoco AW46 is the oil I'm going to use on site as the end user, but it was filled with whatever it was filled with, which is an AW46 oil, but just not Conoco brand, some other brand. So because I look at calcium from hour 0 as being a very, very low value and the trend being very, very flat, I'm not going to say calcium is a problem. All right, I can do the same thing if we look down here at phosphorus. Again, the phosphorus current value maybe doesn't match the new oil reference, but the trend is flat. Same thing goes with the zinc. So you look at those 3 values and you go, all 3 of them are additives, all 3 of them don't match the new oil line. That's just further and further evidence that what we think is the new oil and what we think is the actual oil in the machine, probably not the same 2 products, but consistent product, right? There's been no major shifts in that data to suggest it isn't the right oil the whole time. So let's continue on to the next half of the first page and stop at the next piece of abnormal data. Now, even though it's not alarmed, a lot of people will stop on silicon. and say they don't like silicon because it's doubled in the last sample. Well, whether or not you believe that to be a major increase, let's go with it and say it's abnormal, it doesn't follow the trend. Well, the question is it a cause or an effect? And if you're having trouble deciding, how do I know if it's a cause or an effect? Just think of it this way. Would silicon cause iron and lead to appear? Or could iron and lead make silicon appear? And hopefully you're realizing that, yes, silicon in the form of dust would cause wear, which could create the iron and lead, more so than iron and lead can't make silicon appear out of the blue. So silicon is definitely a cause, not an effect. So we're going to put it in the cause column here. Okay, we keep reading the report, and some people pause on this other fluid value. And they look at the baseline value of 40, and they look at the current values of 118 and go, that's not right. But we have previously determined from the calcium, phosphorus, and zinc that maybe this oil isn't Conoco AW46. So the infrared value for other fluid is going to be different because it is not actually the same oil as the reference sample here. And if you look at the data from the very far right sample, again, what does the data tell you? It's a flat trend. So it's not changing. It's not a problem. We can move on. But then we get to particle count. The whole particle count, we don't need to go through it line by line. There's been a substantial increase in the particle count. Now, this is a very tricky question. This is one I don't expect people to have an answer to. Is the particle count a cause or an effect? So is the particle count a cause and it's driving the iron and lead to go up? Maybe it's related to the silicon. Or is the particle count an effect? That the particle count is the iron and lead particles from the wear, right? So we don't know if we should put the particle count in the cause column or if we should put the particle count in the effects column. So let's leave it as a question mark for now. We'll come back to it once we finish reading the rest of the report. Because again, like I said, don't interpret on the fly. Wait till you get the whole picture. And we haven't seen all the data yet, so we'll wait. Okay, we keep reading down the rest of the report. Everything looks about what we'd expect. I mean, it's a 46 centistoke oil, and look at that. The viscosity is nearly perfect. As for acid number, you'll notice that it's increasing. But what did we say the intervals were again? We said they were 2-week intervals, 4-week intervals, and 4-week intervals. How much is the acid number increasing from the very first sample on the far right? It's increasing 0.02, then 0.04, then 0.04. That couldn't be a more perfect linear relationship to time than I could ever invent. Right? I couldn't make, if I made up numbers that looked that close to a linear relationship, you'd assume I made them up. You'd assume they were too perfect, but this is a real sample, it's real data. Now, why does it not match the new oil line? Again, we've established that. This is probably not Conoco oil. This is probably some other brand of AW46. So again, I can discount that. But when I get to the bottom of the report, I will notice water. And water has gone from 90 to about 400 to over 3,000 to now nearly 7,000 parts per million. It's a major, major increase. Is water a cause or effect? Well, you bet. Water is definitely a cause. So let's put water in our cause column. Now, to finish off the report, we go to the last page, the second page here. You get an analytical ferrography. This is a very forensic type analysis that's done on wear materials and contaminants. It looks at size, it looks at shape, it looks at color. Now, size tells you severity, shape tells you the mechanism that created the particles, and color can hopefully narrow it down to what type of material it is. So generally speaking, just as a short intro to analytical ferrography, the first two on this list here, the first two, rubbing wear and rolling contact fatigue, are about the only two on this entire list that could ever be considered expected or normal. And that's only if the particles are really, really small, like under 5 microns. When you see anything really large in those categories, size-wise, it's a problem. And if you see anything in the remaining categories, the other 10 categories, it's definitely a problem. So my point is, whenever you see data on an analytical ferrography, barring the first two being small-sized particles, anything else is going to be considered abnormal, regardless of how much is there. Right? It's material that shouldn't be there. It indicates wear modes that typically aren't expected, or at least a severity that isn't anything but normal. So what's the first one we're going to consider abnormal? Well, rubbing wear. Why? It's a very high level of it, and the particles are very, very large, right? They're almost visible. So is that a cause or an effect? Well, as I said at the beginning as a clue, wear is just an effect. So we'll put that under effects. Okay, we see sliding wear. Sliding wear is never normal, regardless of the particle size. That indicates, low lubrication film and all kinds of issues. But again, we're not going to interpret as we go. We just see there's a high level. We see the particle size is very, very large. In fact, I don't know, large enough we can maybe get the first 3 digits of the part numbers off that. But it's bad. Is it a cause or an effect is all we need to decide. And again, it's a type of wear. So we're going to say sliding wear. It's another effect. Okay, keep going down the list. You're going to find corrosion. Corrosion, is that a cause or effect? Well, it's, again, just an effect. Bet you it's got something to do with that water, though. But as we continue along, we'll find the next thing, dark metallic oxides. This one here, generally speaking, those are created when 2 surfaces come under such extreme pressure and contact, and that as they rub together, they temporarily weld to each other. And as they weld, the temperatures that are created are high enough to cause annealing. So that's why it darkens. That's what we call it dark metallic. But then as the surfaces continue to move across each other, they will tear the material from one off the other. And that exposes a fresh metal surface and creates an easy target surface for oxidation. So dark metallic oxides. Point is, very, very bad wear mechanism. Question is it a cause or an effect? Again, it's a type of wear. We're just going to call it another effect. Okay, then we go down the list. The next one we see is red oxides, which is a very fancy way of saying rust. Cause or effect? Again, just another effect. Last one on the list, though, is dust and dirt. Dust and dirt here, is that a cause or an effect? Well, it's probably a cause. I'll bet you it's even related to that silicon value, right? But just to make sure we didn't lose track of anything, let me remind you, we did not finish where we put particle count, right? We left it as question marks. Now, knowing that we've got high silicon, knowing we've got dust and dirt, do we think the particle count has more to do with contamination, or do we think it's got more to do with the wear debris? And even if you're willing to say that a significant amount of the particle count is from the wear debris, that's fair, I can't dispute that. You have to admit, it seems like some of that particle count is probably also the silicon and the dust and dirt, right? However those are related. So why don't we take our list, we'll leave particle count under the cause, but we'll take it away from effects. Okay, so now we've reached the end of the report, the end of step 2. We identified everything that was causes or effects. And I said the very last thing you'd see is that they'd group the causes into 1 or 2 groups. So the first group is that the silicon, the particle count, and the dust dirt all belong together. They're probably all interrelated. Water, on the other hand, may be something different. But these are the ones we're going to focus on, not these ones. And that's how we get the report nice and quick. So now all we need to do is decide what to do next, right? What is our follow-up action for a bearing that's got high silicon, high dust dirt, high particle count, and water, right? And I'm just, show you the first page of the report here, remind you again, it's a bearing, right? It says so at the top. And you think logically, what is the most common reason that you get those 2 different things happening together, right? It's just a little bearing. It has no real internals to it. It's not a combustion engine, as I'm getting at. Like, combustion engine can generate its own soot, can generate oxidation byproducts. There's a lot of things that generate inside the engine that could come into contact with the lubricant. This is just a little bearing spinning away on its own. So probably the simplest way anyways, that this bearing received any form of contamination, be it dust, dirt, silicon, whatever you want to call it, and moisture, I'm going to wager it's got something to do with the breather. So hypothetically now, just saying it's the breather, well, either the breather's damaged or the breather's inadequate, right? So it either needs to be replaced or repaired. And it's one of those common things that comes up many, many times that we just deal with. OEM breathers are usually not very good, and they need to be upgraded to a slightly better one, or maybe we're dealing with slightly better ones and they need to be upgraded to a more premium one. Got to keep the system clean and all that kind of good stuff. But this report here, it's probably the first thing we're going to do is send somebody out there to inspect it, to confirm that the breather is in place and functioning, that it's adequate. I mean, we can check for all kinds of other things while we're just doing a quick visual, make sure the fill cap's on, the dipstick's in, the seals are, reasonably good shape. All kinds of things. We're just basically looking for, is there any way contamination could have gotten in? And I'm going to wager that whatever's wrong with this bearing is going to be fairly obvious, just because of the way the trend spiked up so quickly that something has changed in this bearing, that it was following a fairly normal trend and then all of a sudden went kind of sideways. So something's gone wrong, right? A fill cap wasn't put back on, a dipstick popped itself out, a breather's become damaged or is loose or is, just overwhelmed, whatever. And we could have a longer discussion on this one, but in the interest of time, I'll just keep things moving along. But here's my bigger point that I want to make with this report, now that you've seen sort of the format and why we focus on causes, not effects. Because we don't need to worry about where the iron and lead's coming from if we don't know why it's coming, right? We need to understand it's probably related to contamination. If we can solve the contamination, we will prevent further wear. Right now, the question becomes, is it too far worn to keep it in service? That's not for us to decide at this moment in time, and I don't know that we have enough data to do that. But we do have enough data to answer this question here. And if you want to throw your answers in the chat, by all means, but I'm thinking it's more of a rhetorical question that most people are going to arrive at the same answer. But you can see how you fare with your answers. Question is, if I call this one sample number 1, because it's the first sample on the report, and the next one number 2, and the one beside it number 3, and of course the last one, I'll call it number 4. Understand it's a bit of a trap question, but if you'd taken the time to read every report when across your desk, whether it was normal or not normal, all those kinds of things, whether it's lit up in green or lit up in yellow or red or whatever colors they use, if you'd read every report as it came to you, when it came to you, when would you have actually caught the problem? And I'm hoping you're not picking sample number 4. But if you look at the data, look at iron, look at lead, and if I flip back and showed you water content as another big key indicator as well, chances are what I'm expecting everyone to come up with as an answer is you would see that it was that third sample showed where that trend went from a fairly straight trend to suddenly taking off and going up in a steep way. And that's the whole point here. Had we read every report with that kind of eye, looking for abnormal values, we could have predicted that this was going to happen. And that this fourth sample here was no surprise to us. But instead, waiting for the fourth sample to cross all the thresholds and alarm the iron, alarm the lead, alarm the particle count, alarm the water content, right? We may be in a position where we're forced to change the bearing or we're forced to change the oil because we can't leave it in continued service. So with that, you get a bit of a flavor for how this works. So let's just go through the second example. Like I said, I'll do this more in normal time, not take so long to get through it. And this will give you a bit of an idea here, sort of the speed, kind of the pace that it happens at. So here we go. We start with this one. I'll pull out my laser pointer again so you follow along. But it is another bearing, just a plain bearing. It's using an RNO 68. What do I know about RNO? RNO type oils typically don't have additives that show up in oil analysis. Okay, they are made from chemicals that don't exhibit a whole lot of calcium, phosphorus, zinc, magnesium, all those things. So I'm expecting to see what looks like no additives. It's a 68, so it should be 68 centistokes. Tells me it's a 5-gallon sump, it's not very big. Okay, we see the dates, we confirm it's us, we read the problems, excessive wear, excessive particle count. We see 2 comments related to this. Big thing though, and I want to draw this to your attention with that green arrow, this sample was taken post-failure. Okay, so we don't have to figure out if it's going to fail. It did fail. We need to see if the oil analysis data tells us why it failed. Now, I'll just take away that green arrow here for a second. When you go through this report, and like I said, I'm going to do it more in real time now, understand that I've removed all the alarms. I took away anything to do with color on this report so that it wouldn't focus you on anywhere you didn't need to. It's to help you train, read every single line of the report. So we do read every line of the report. We look at the sample dates here and we go, look at that. It took 14 months between the first and second sample, then 18 months, then only a few weeks. Okay, very inconsistent. I don't know what I can glean from that. We look at the hours that are being reported. It was left blank 2 times. That's why it says 0 and unknown. And then the other 2 times, I don't know if they knew what they're writing in there. They don't make sense. Right? I can anticipate 38,000 hours on a machine. Sure. 5 years continuous service makes sense. 38,000 hours on the oil, I don't believe in that as much. But then the hours went down on the oil and on the bearing. Does that mean there was a new bearing with new oil? I don't know. It's a bit weird. It's a bit wonky. But it does indicate we should probably expect a dip in the data at that moment. So who knows? But anyways, we read through the report, and like I said, doing this one kind of in real time here, what's the first thing we notice? Right, high iron. Cause or effect? Well, you know where this is going. It's an effect. Next thing we notice, high copper. Is that a cause or an effect? Again, you should be no surprise here. It's an effect. Keep going. We got another wear metal here. We got high lead. Lead, a cause or effect. Again, it is an effect. Okay. Luckily, though, we can't skip over aluminum. That's a flat trend. But you look at the next one here and go, whew, that's pretty high, right? A lot of tin in there. But again, cause or effect? Just an effect. Keep moving. Okay, we keep going down the report and we get to calcium, much like we did in the previous example, but now we don't expect to find calcium, yet we did. That's unusual. And if you look at the history of the trend, it wasn't always there. The increase in calcium seems to come at a time where the increase in wear has happened. That's weird. So is this a cause or an effect? Seems like it could be a cause, right? Same logic goes down here. We got phosphorus. Phosphorus shouldn't be there, not in those levels, and it has appeared and is increased. Cause or effect? We're going to call that one also a cause. All right, keep going down the report. We're going to move to the next page here. Everything looks fairly decent until we get to particle count again. So particle count looks very, very high. And when you see it all nines like that, it means it maxed out the instrument. So that's an extraordinarily high particle count. Again, question is, where does it belong? Cause or effect? Right? That's a tricky one to answer, isn't it? So when you think about this one here, we'll just, leave it, come back. So next page, what do we see on analytical ferrography? Again, a lot of rubbing wear. Shouldn't be there, cause or effect. We're going to say, again, it's just an effect. Much like the previous one, a lot of sliding wear. Again, larger particles. Doesn't look like it's a good thing. Is that a cause or an effect? Again, we will decide that this one should probably just go with the others. We'll put it down as an effect. And then we get to the very bottom of the report, we see dust and dirt. So dust and dirt is abnormal. Where do we put that on the cause or effects? Well, that one definitely going to be a cause, right? So we'll put that here. So just to make sure we address everything, much like the previous report, we do need to address that particle count. We need to pick where does it go. Now, seeing that we actually have high dust and dirt, we can maybe attribute that it's not all entirely wear metals. So again, much like the previous example here, we can decide that we're going to put that one under causes. So now that we've finished the end of the report, and as you can see, it took less than 2 minutes, we grouped the causes. Probably calcium and phosphorus are related to themselves. Probably dust, dirt, particle count are related to themselves. 2 different groups of causes. These are the ones we're going to focus on again, not the other ones. So now here's where I'm looking to see if the audience has a little bit of input. See if you can guess what went wrong. Right? We know it failed. We know that it failed, right? We need to know why did it fail. So here's what I'm looking at. You need to think of one reason, one cause, one set of events that had to occur that would have given us the following. It needed to give us elevated calcium phosphorus. Now, generally, that means another lubricant got in there, right? That's a common answer for where those would come from. But you also need to account for the fact there's no change in viscosity. The viscosity of that sample was 67.9 centistokes, nearly perfect, almost exactly a 68. You also need to figure out what could have caused an increase in dust and dirt getting in there, the increase in particle count. And remember that generally speaking, silicon means it's from dust. Dust and dirt could be both silicon or silicon aluminum combinations. We didn't really see that, but elemental spectroscopy measures different sized particles than particle count does. So the fact that it shows up on particle count but not wear metals tells us it's larger particles. So we got big particles, and it shows up in the analytical ferrography, which is also generally larger sized particles. So we got a lot of big hunks of dirt in here. Generally, this means contamination from airborne sources, but what I'm getting at here is pretty severe contamination from airborne sources. So let's see if there's been any guesses here as to what went wrong, what happened to this particular machine. So we have to appreciate that this one event would have caused a very sudden, very catastrophic failure. So with that, just look over here. I see one comment here says, report does not mention anything about varnish and varnish potential markers. For low-speed machines, this report would be adequate, but for high-speed machines, it would fall short. What are your thoughts on the above? Well, if you're asking me whether or not they should have done an MPC type test or an ultracentrifuge, I would agree with you that yes, If it was a higher speed, higher temperature machine, that would be warranted. I would say in the particular example we're talking about, though, whether there is or is not varnish is irrelevant. There is clearly a contamination issue that's probably what drove it to its failure. What I was hoping to see in the audience was maybe somebody might come up with a guess as to why it happened. How did it happen? I think one of the most common answers I get to that question is a lot of people will sit there and say, well, if the wrong lubricant got in there, they must have topped it up with the wrong product. Well, that's an easy answer, but you have to qualify that. And so most people go, well, okay, they topped it up with a dirty funnel or oil that's been sitting for a while. It's in a dirty container. And I go, okay, fair enough. It would have different additives. It would have contamination. But here's the third thing. It has to have the same viscosity, because the viscosity did not change. So you have to think to yourself, if I add the wrong oil, but it's the right viscosity, and it comes through a dirty funnel or with a dirty container, and the additives are slightly different, do I definitively think for sure that would cause a catastrophic failure? And most people pretty much renege on that answer and say, nah, I don't think that actually is the answer. So here's my point. Like I said, it's a bit of a trap question. If you were the end user, you would actually know a little bit more about this. So you would know everything I already previously mentioned. That's a given. That's just based on our interpretation of the report. But now add in these two details. You know that it operates in a very, very dirty environment. I mean, just airborne contamination everywhere, but it's dry, right? Very dry environment. So it's a lot of dust is what I'm getting in the atmosphere. But you also know that it is in a bearing housing that has greased seals. See if that now prompts the right answer. And just to really help you out here, here's the grease they're using to grease the seals. I mean, oil, RNO 68 is going into the bearing, but they're using this grease. And now I know you can't read that clearly because the picture's a little fuzzy anyways, but if I zoom in, you can actually see that it's in the EP grease that's a calcium sulfonate. And if you're still not putting all the points together, let me show you a picture of the actual bearing. From the manufacturer's website in a perfectly clean environment. But my point is, if you look at this, there is the Zerk fitting on the one side of the bearing housing. There's of course another one way over here. But you can see this has grease seals. And if we're using a calcium sulfonate grease, how could that explain why the bearing failed? Well, I think the answer is that they did grease the seals and they put the right oil into the bearing. That was all done correctly. But if they over-greased the seals, they would have failed the seals, right? They would have pushed the lip seals out, and therefore the seal would not be sealing, so dirt and dust and all that could get in, which would have led to all the abrasive wear and would have led to the failure. Now, given that the oil would allow the dirt to migrate in that way, so would some of the grease, right? If you're going to pump in excess grease, some of the grease is going to go to the outside, but some will go to the inside. And it would not take very much grease to make a big jump in the calcium and the phosphorus values, being this EP grease, there's your phosphorus, being it's a calcium thickener, there's your calcium, but being that it's grease and only just trace amounts of grease, it wouldn't change the viscosity. So again, if you focus on the causes and ignore the effects, if you can figure out where the causes are related to each other, you will solve all of the effects. Now, this bearing already failed, so we can't save the bearing at this point, but we do recognize that going forward, we need to be a little bit better about our greasing protocols here to prevent people from over-greasing the next, new rebuilt bearing with new seals in it and everything, so that we can avoid a repeat of that same fault. So my point is, to wrap up our discussion here, what I've hopefully shown you is a simplified way to interpret your reports, to not focus on 300 different pieces of data, trying to piece them all together like a jigsaw with one piece coming out at a time, trying to paint yourself a picture. Knowing which are the most important pieces, knowing how to effectively, methodically get through a report quickly to summarize which ones are the ones I should be focusing on. So you're trying to identify, this is the key thing, right? The root cause to the problem. You're trying to make sure that oil analysis is predictive as possible, right? It was intended to be predictive. And many of us have gotten complacent and just wait for the alarms to go off, which turns it into reactive technology, which is, doesn't help anybody. But hopefully, like I said, by being so quick and methodical with this, you now have time to read every single report that crosses your desk and you will hopefully improve your program's effectiveness. You'll get your reputation up because people think, wow, they actually can tell things from the oil analysis report. And of course, one of the key things most people are looking for is a return on investment, right? That the program pays for itself. And I think you'll find if you start looking at your reports a bit differently, they definitely will. So with that big deep breath here, I am done. I do thank everyone who took the time to participate in this webinar. Thank you for watching. I've included our website if you want any more information, or my own email address if you'd like to contact me outside of this presentation. Of course, I am available in the Slack channel for upkeep as well. So if I realize if I took too much of your time and you got to go right now, I'm certainly glad to talk to you later. But now I'll turn it back over to Heather and see if there's anything we need to address from the questions of the chat.
That is wonderful. I do know we are up at our hour. Evan, thank you so much for a wonderful presentation, really engaging and super interesting new approach to kind of get the most important information the quickest. I have a couple of questions from the chat, but out of respect for everyone's time, I do think we should take those offline. Sure. I will be sure to send you the questions as well as post them in the thread with this replay when it is released tomorrow in the Slack channel as well. If you do want to ask Evan your questions directly, his contact information is here, and you can go ahead and send him an email with your question in regards to the presentation. We're getting a bunch of thank yous now, so I think that'll just about wrap us up for this morning for me. Thank you all. Thank you, Evan, again, and we'll see you next time.
All right. Thank you.
Thank you.